So, I was thinking about the ownership model in Rust this weekend. It's fascinating how it helps prevent data races and memory leaks.
Yeah, it seems really strict, but effective. How do you keep track of all the borrowing rules?
The key is to understand that each value in Rust has a variable called its owner. There can only be one owner at a time. When the owner goes out of scope, the value is dropped. This makes sure there are no dangling pointers or double frees.
That sounds like a lot to remember during development. Does it slow down coding?
Initially, yes, because you have to think about lifetimes and ownership transfers. But once you get used to it, it actually speeds things up by avoiding common pitfalls that other languages struggle with. Plus, the compiler guides you with clear error messages.
I see what you mean. It must make debugging easier too.
Absolutely, because most of the errors related to memory safety are caught at compile time rather than runtime. And let me tell you, when you first encounter those error messages, they might seem daunting, like cannot borrow as mutable more than once at a time, but after a while, you start to appreciate them for their thoroughness and accuracy.
That's true. I've noticed that pattern matching also feels very powerful with Rust.
Definitely. Pattern matching combined with the ownership model allows for some elegant solutions to complex problems. You can destructure values safely knowing that the ownership rules ensure everything is handled correctly without causing undefined behavior.
It does sound like a robust system once you get the hang of it.
Exactly. And once you're comfortable with it, writing safe concurrent code becomes much more straightforward compared to languages without such strict controls over resource management. It's like having an extra layer of security built right into the language itself.
Makes sense. I guess practice will help internalize these concepts better.
For sure. And every project gives you another chance to refine your understanding. Have you seen any interesting projects using Rust recently? Actually, speaking of refining understanding, have you thought about how ownership in Rust prevents null pointer dereferencing?
Not really. How does that work exactly?
Well, in Rust, the ownership model ensures that variables are always initialized before use. Since every variable must have an owner, and that owner is responsible for its initialization, you can't accidentally have a null or uninitialized pointer.
So it's like the language forces you to handle all cases properly from the start?
Precisely. Unlike some languages where you might end up with a null reference somewhere due to oversight, Rust's strict type system and ownership rules make sure that pointers are always valid when used. This means no more crashes due to accessing a null pointer.
That sounds like it could save a lot of headaches during debugging.
It absolutely does. The compiler enforces these rules, so by the time your code compiles successfully, you've already avoided a whole class of bugs related to null pointers. And because of this, you can write safer concurrent programs without worrying about race conditions leading to invalid states.
It definitely seems like a proactive approach to error prevention.
Exactly. By design, Rust shifts the burden of handling these issues from runtime to compile time. This not only makes your application more reliable, but also lets you focus on solving actual problems instead of chasing down bugs caused by null references. Speaking of concurrent programs, have you thought about how ownership and borrowing work in multi-threaded applications?
Not really. How does that differ from single-threaded code?
In multi-threaded environments, ownership and borrowing become even more crucial. Each thread needs to respect the ownership rules to avoid data races. For example, if multiple threads try to modify the same data simultaneously, Rust's ownership model ensures that only one thread can have mutable access at a time.
That sounds like it could get complicated quickly.
It can be tricky at first, but once you grasp it, it makes managing shared state much safer. The mutex type is a good example. It provides mutual exclusion, ensuring that only one thread can hold the lock on a piece of data at any given time.
So it's like locking mechanisms in other languages, but integrated with the ownership model?
Exactly. And because of this integration, you get compile time checks that prevent you from making unsafe decisions at runtime. You don't have to worry about forgetting to unlock a mutex or having deadlocks because the ownership rules enforce correct usage patterns.
That makes sense. It seems like Rust handles concurrency in a way that feels both safe and intuitive once you understand it.
Absolutely. Once you're familiar with how ownership and borrowing interact with threading, writing concurrent code becomes much more manageable and less prone to subtle bugs. Plus, tools like ARC, atomic reference counting, allow for safe sharing of immutable data across threads without sacrificing performance.
It definitely sounds like a robust solution for handling concurrency.
Indeed. And as you work more with it, you'll find that these principles help you write cleaner, more maintainable code overall. Thinking about how ownership and borrowing manage concurrency leads me to another interesting aspect: how Rust achieves memory safety without needing a garbage collector.
Right. That's something I've always found intriguing. How does ownership play into that?
Ownership is the cornerstone of Rust's approach to memory safety. Instead of relying on a garbage collector to clean up unused memory, Rust uses its ownership model to ensure that memory is managed deterministically at compile time. Each piece of data has a clear owner, and when the owner goes out of scope, the data is automatically delocated.
So it's all about automatic cleanup based on scope?
Exactly. This deterministic cleanup means you don't have to wait for a garbage collector to run periodically. The ownership model ensures that resources are freed immediately when they're no longer needed, which can lead to more predictable performance.
That makes sense. It seems like a very precise way to handle memory.
It certainly is. And because the compiler enforces these rules strictly, you get strong guarantees about memory usage. You don't have to worry about common issues like double free or use after free errors that can plague other languages.
It sounds like the ownership model really ties everything together neatly.
It does indeed. The combination of ownership, borrowing, and lifetimes allows Rust to provide high-level abstractions while maintaining low-level control over memory management. This balance is what makes Rust unique and powerful for systems programming.